Greetings and welcome to a new video about analog electronics, and we continue with our diode circuits. In this case we will look at a special diode which is a Zener diode. And we'll look at the theory and also the examples to support those theory, and it will be a complete topic about the Zener diode. Of course we will look at their calculation and also verify those of them using the SPICE simulations. Okay, first the outline. This is the outline for this video about the Zener diode. We'll look at the current voltage characteristics of this Zener diode. Also look at the breakdown characteristics, which is a fundamental part of the Zener diode. And also look at the equivalent circuits to work out the circuits. For example, we'll give example 1 and also calculate the specific parameter, which is the Zener impedance. We also look at the temperature effects, and again we'll look at example number 2, which also illustrates this. The power dissipation, also the power derating, one of the important topics also in Zener diodes, also will be illustrated first with theory and then with an example. Then we'll look at the Zener diode datasheet information, also important to consider if you want to choose a specific Zener diode for your application, and also we'll look at an example for that. Then we'll look at the Zener regulation by changing input voltage, so there will be a variable input voltage, and again we will support that with a numerical example. In a similar case, the regulation, but then using a load resistor which is then variable, so we get a regulation with a variable resistor. Okay, this is the outline and we will work it out step by step. Let's first start with the current voltage characteristics of this Zener diode. So this is actually the current voltage characteristics of any diode, but this is specifically now discussed for the Zener diode, and the Zener diode is given by or used as this symbol. You can see the Z here, sort of the Z, and this is the cathode and this is the anode. So this looks like a simple signal diode, only this part is different. You can see several parts. This is the breakdown. It is the breakdown voltage for the Zener diode. So it is actually used in the breakdown region, not on the forward region. You can use it in the forward region, but it is specifically designed for the breakdown region. And this part is called the reverse breakdown region. And this is the breakdown voltage, also called the Zener voltage. So the Zener diode is a PN junction device. So it has a P and an N layer, and it can be designed using a silicon or any other semiconductor or a compound of that one. It's also designed, as said, to operate in the reverse breakdown region. So that is specifically done. So it is a high doped device. So at the reverse breakdown, the Zener voltage, VZ, remains almost constant, almost, not exactly, while the current changes drastically. So the current can change here, let's say from 1 milliamp all the way to 100 milliamps, but maybe the voltage can be around 5 volts, maybe a little bit up, a little bit down. So that is approximately 100 or 200 millivolts up and down. So there's kind of a very large change in the current, but very small change in the voltage. That is also the reason, also the purpose of this Zener diode, to make the voltage at very constant level. Now the breakdown voltage, VZ, is determined by the doping concentration. So if doping concentration, for example, is low, then you have a high breakdown voltage, because when you have this breakdown voltage, you look at the doping concentrations. And if you go to the high doped concentration, then they will be lower. So, and specifically for the Zener diode, it is most of the time highly doped, much higher than a signal diode, which you use for just rectification. And what you also see is that the steeping here, this line, is steeper than for the low doped device. So larger doping concentrations result in smaller breakdown voltages. So you can design that. So you can, if you have, let's say here 6 volts, you want to increase that, you can lower your doping concentration, you can go up to maybe 10, 11, etc. Okay, that's for the first about the current voltage characteristics. Now let's look at the specific breakdown. That is really important. We have now 2 types of reverse breakdown. One of them is the avalanche in these PN junctions. And this is then given here in a sort of a pictorial way. It is not the exact way what's happening. You have the P and the N region, and in between you have the space charge region. That is actually the region where you have the depleted of the charges. So this is the part P where the holes, the positive say charge, are major, so they are actually here in domination, and the N part is where you have the negative charge, so the electrons are dominating here. But when you have electric field, which is then reversed, because from N to P, that is what's happening, then you can create such a high electric field, then this charges here in the depletion region can gain a lot of energy. So that's actually what's happening. So a high electric field, and the carriers crossing this space charge region gain a sufficient kinetic energy because of that high electric field. So what happens now, if you have a charge which has a very large high kinetic energy, it can collide with another one. So covalent bonds are broken during the collision process, and then you can generate by opening actually a electron hole pair. That is called the generation of electron holes. So generated electron hole pairs can themselves again be involved in the collision process, generating additional electron hole pairs. So you get a chain reaction, which is called an avalanche. So you have a high field, electric field, that will cause the charges to get sufficient kinetic energy. They collide and then produce or generate electron hole pairs. And those electron hole pairs, new pairs, will again collide with a new particles, and then will generate again electron hole pairs. And this is called the avalanche process. We have also the Zener process or Zener breakdown. That is the part where we have in the Zener diodes most of the time, and as a result of tunneling. So you have a really thin, this part is really thin, and that causes the charges to able to tunnel. That's caused because of high doping. So the manifestation at very high doping concentrations. So reverse bias current due to a breakdown must be limited, of course, because if you don't limit that, you can burn up your device and permanently have a damage. So you have external leak circuit, let's say a simple resistor, that can lower the current flow through your device. That is very important. So it's not just connecting your battery or your source to the Zener diode and you will have a constant voltage. So you need to really lower that or limit that. Now this is the circuit where we can use it to limit the voltage across the Zener diode. So we have now, let's say, a 15 volts source, and you would like to connect them to a Zener diode, which will then regulate the voltage across some node. And if you just connect that VS to the Zener diode, you'll have 15 volts, and it will destroy this Zener diode because it is designed for 6.8 volts. So you cannot have that. Now, in order to have here a sufficient voltage here, or let's say the nominal voltage, you can reduce that 15 volts by getting this resistor in a limiting form, and then you will have 8.2 volts across this. So 15 minus this 6.8 will be then 8.2. That will be then across this resistor, and the current flow will also reduce because of that resistor. Okay. Let's also look at the characteristics in more detail, because this part is important. We can also look at the forward part, but the reverse part is important. You can see the following parameters. We see the VZ, which is defined at the IZ, and that's also called the Zener test current. So it is that the current which is then for this specific voltage. This is, by the way, also given in the datasheet. You have also the minimum value, which is called the IZK, which is the Zener minimum or Zener knee current. So it is really the smallest possible Zener current you can have in order to have small changes with respect to the nominal Zener voltage. You also have a maximum Zener current, which is called IZM. So you have three parameters, and in between you have this VZ, which goes up and goes down a little bit. We can see how large this current is changing, the Zener current, with respect to the small changes here in the voltage for the Zener diode. So the Zener regulation diode operating in the breakdown region acts actually as a voltage regulator, keeps the revert voltage essentially constant, essentially not perfectly constant, but very close to the constant value you want to have. And the Zener diode parameters are the minimum required Zener current, which is then to keep that in breakdown. So if you go a little bit lower, then it is not anymore in the breakdown region, and it is not anymore the voltage regulator condition. You have also the maximum allowed reverse current. That's also required because if you go higher, then you can also cause permanent damage, so you need to prevent that. Now there's also a part where you want to keep it constant, almost constant. That is actually between the IZK and IZM. That is the region where you have the reversed current range. This is the nominal VZ, nominal Zener voltage. This is the nominal Zener current, or Zener test current. Nominal Zener voltage is specified in the datasheet, and that is then at that Zener test current specified. Okay, let's now look at the equivalent circuits. Very important. We have the ideal Zener diode model, so where it's just simple, and we also have a practical part. So first start with the ideal one. This is the diode, the Zener diode, the symbol, and this is the simple model. It's just a battery. What does it mean? You have the anode and the cathode, and between anode and the cathode you have this battery, and that means if you go down, let's say with your voltage in the reverse direction, at some point you will reach that VZ, and it will stay at that VZ, and the current will be then infinite. That is the simple diode model, Zener diode model. This is most of the time okay. You can just work out with this. The first order approximation will do the job for most circuits. But if you want more accuracy, you can go for practical Zener diode model. Of course, then you have more parameters. And this is the parameter you have. So this is the Zener diode. Now you have, in addition to the battery, the Zener impedance, also called the Zener dynamic resistance. And in between these two nodes, now the actual Zener voltage is there. So this is the Zener voltage when there is no current flow, let's say, and this is the additional parameter which will lower actually, or increase depending on the current flow, the voltage across the terminals of the Zener diode. So outside the Zener diode, you only see, of course, the cathode and the anode, or the leads, and in between there is a modeled Zener resistance, or Zener impedance, or dynamic resistance. And that can be measured or determined from the graph. You can see that here, because this is perfectly vertical. That means there is actually the slope is infinite. If you look at this, slope is not infinite, so you can see this voltage here is the changing in the Zener voltage, and this is the Zener current change. And that change divided by that change will give you the ZZ, which is the Zener impedance. And again, between the limits of the minimum and the maximum Zener current. And this practical model is more suited when you want to have more accuracy. Okay, so the Zener impedance again given by this changing Zener voltage over the changing Zener current. Let's look at an example. Always handy to illustrate the concept, so what is really happening. We have now this IV plot of the Zener diode given, and the change in the Zener voltage, and also the change in the Zener current is given. You can see that in the plot. Now we want to have, looking at this graph, the Zener impedance. So that is really important, and let's discuss this. Let's calculate how we do that. Now you already see that VZ is 40 milliamps. So the solutions, this is given by the for the formula. So the change in the Zener voltage is 40 milliamps, 40 millivolts, I must say, 40 millivolts, just 40 millivolts. For the Zener current, the change in that is 4 milliamps, because it goes from 11 to 15. This is just 2 points here, not the minimum or the maximum. You can just pick any point here. This, in this part, your Zener impedance will be then determined. Now, when you substitute now these two values in here, you will have this expression. So 0.04, 40 millivolts over 0.004, 4 milliamps, you will get 10 ohms. That's the value for your Zener impedance. By the way, this is a maximum. It can be that this is steeper or different slope. In this case, by the way, it is less steep, so you will get more resistance. So that is important. So you need to keep actually your line, your definition for the Zener impedance in this part, for the operating and the regulation. So this 10 ohms, that's actually the answer for this example, looking at the graph. So you can pick any graph from the datasheet and do the exact same. Okay, let's now look at the next topic, which is the temperature effects. That's very important. We all start with the practical Zener diode again. This is the model. And now the temperature coefficient given by TC is very important, because if you have a device or a system which regulates between very small and very large temperatures, then this temperature coefficient can have an effect on the actual regulation of your voltage. And this is the plot that will describe graphically what's happening if the temperature is changing. The blue line is the part where you have the device at 25 degrees. Now, if you look at the breakdown, it is here approximately for the blue one, and you can also see the forward voltage volt approximately 0.7. This is the general basic signal diode IV curve. When you go to higher temperatures, so 25 degrees plus, let's say 40 degrees, so up, then this will go shift to the left side. But this is only happening because this is a negative temperature coefficient. So if it is a positive temperature coefficient, it will go to the right side. But this is just an example for a negative temperature coefficient. So if you go to the left side, so the red curve will then shrink actually from left to right side, so it will then compress itself. So the breakdown voltage will change, it will be smaller, and also the forward voltage will change. That will of course have an effect for your breakdown voltage, because that will determine your voltage regulation. So this is important. And that will then given by this expression. So the change in the Zener voltage, the breakdown voltage, is given by the temperature coefficient times the change in the temperature. But the temperature coefficient here, is given by the volts per degrees. And this Zener diode is given by the volts. And the temperature is given by degrees. You can also have it in Kelvin, it doesn't matter. In ratio, it is the exact same. Okay. But the variation can be also given in this format. So that is then given by the delta Vz. Now you use a nominal voltage Vz from the datasheet, again a temperature coefficient, and this is the changing in temperature. But now the temperature coefficient will be given in a different unit, which is then percentage over the degrees. And that will be illustrated shortly in an example. Okay. So, example 2, Zener diode temperature effects. Now, let's say we have a Zener diode. It has a nominal Zener voltage of 6.7 volts, but defined for 25 degrees. And the Zener diode has a positive temperature coefficient. And this is then the given. So it's 0.08% per degrees. Okay. So we would like to calculate the Zener voltage, Vz, of the Zener diode at 100 degrees. So we will go up from 25 to 100. So what's happening? How do we calculate this? Now the variation in the Zener voltage must be now calculated using this formula, because we have now the percentage over degrees for the temperature coefficient. It's positive, that means it will go up. So again, the parameters in this formula, temperature coefficient, also the change in the temperature. So if I now look at a temperature coefficient, which is 0.08% per degrees, I need to convert this percentage to a scaling or vector. So it will be a scaling here, that will be then divided by 100, will be then 0.0008 over degrees. So the change in temperature is 75 degrees, because 100 minus 25. Then we have, looking at nominal voltage, because this is nominal voltage, this is the 0.0008, and this is then 75. And now if you substitute the values, you will get 0.402 volts or 402 millivolts. So the Zener voltage for this Zener diode at 100 degrees will be then, this Zener voltage at 100 degrees will be Zener voltage at 25 degrees plus this additional change. Why plus and why not minus? Because of the positive temperature coefficient. If this was, for example, a negative temperature coefficient, then you should do here a minus. And then you will get this, and the result will be 7.1 approximately for your Zener voltage. So you can see it's you make your temperature 4 times larger, and you go up by 0.4 volts up in this case. Okay. Next part and next topic is the power dissipation and also the power derating, also very important. The power dissipation. Now for a Zener diode, they are specified to operate at some maximum power, so at maximum power or below that. And that is then given by the maximum DC power dissipation, which is then called PZ maximum. This is also found in the datasheet. DC power dissipation is then given by this formula, so it is PZ is equal to volts times the current, so the Zener voltage times the Zener current. So these are the parameters here, and these are the rated Zener voltage and the rated Zener current from the datasheet. So if I want to look at the power derating, I would like to know how much power I can dissipate when the situation changes. So if the temperature is changing, this 50 watts actually for this case, for power dissipation, is not anymore 50 watts. So you can see after 75 degrees, it will change. So the maximum power is valid at or below a certain specific temperature. So if I look at the maximum power, it is reduced above that specific temperature. In this case, it is linear, so it is a first order approximation. It could be, of course, more complicated. So for this case, the power derating factor, PDF, is expressed in watts per degrees. So if I look at the slope, I can calculate that. Now, for this case, larger than 75 degrees, there's 0.5 watts per degree. So you can see this slope has then, this line has a slope of 0.5 watts per degrees. You can see that actually because it goes from 50 watts all the way to 0. When you increase it from 75 to 175, so it goes up by 100 degrees and it goes down by 50 watts, or 50 watts over 100 degrees, it's 0.5 watts per degree. So that's correct. The maximum derated power is then given by this formula. So we have some maximum power that you can dissipate in, let's say, the condition below that temperature. And when you want to go to the derated power, so the power lower due to the temperature increase, then you have the PDF, which is then the power derating factor, which is then this value or any other value from your Zener diode times the temperature change. So these are the parameters in this formula. All right. Okay, let's now look at an example again. Zener diode power derating. We have now a Zener diode which has a maximum DC power rating of 500 milliwatts, but then at up to 40 degrees. So after that 40 degrees, it will change. Now, Zener diode has a power derating factor of 4 milliwatts per degrees. Now, we would like to calculate the maximum power that this power the Zener diode can dissipate at 80 degrees. So if I increase that by a factor of 2 the temperature, what happens? Okay, let's see that. The solutions. The maximum derated power is given by this formula, so we only need to insert here the required values. So we see these are the parameters. The PZ max is 500 milliwatts, so 0.5 watts. The delta T, which is the change in the temperature, is in this case 40 degrees, so 80 minus 40. And I have also the PDF, which is given by 4 milliwatts per degree, so 0.004 watts per degrees. Now then we have the following. So the PZ, the Zener diode power derated, is then given by this. Now if you work it out, you see you go down from 500 milliwatts down by 160 milliwatts, so that will then result in 0.34 or 340 milliwatts. So it is then reduced. So you will reduce the maximum allowed power dissipation in the Zener diode. This is a part of the datasheet of a Zener diode type. We have this series, and you can see here the absolute maximum ratings. Now you can see, read here the power dissipation, the maximum, which is 500 milliwatts, the PZ max. You also see the derating above 50 degrees, so that is 4.0, so 4 milliwatts per degrees. So above 50 degrees in this case. Now there's also other two parameters we haven't discussed, but it's also important, the total or storage temperature range. So we can store your device between these two temperatures. Also the operating junction temperature range is in this case given and is exact same as the storage range. Okay. You also have the maximum Zener current which is required, but it's not given in the datasheets. If this is again a part of that same datasheet which we require, you can see several types here. And if I look specifically, for example, the 1N5222B, which is given here in green box. And it has the nominal Zener voltage, and from the maximum power dissipation I can calculate the maximum Zener current using this formula, just the formula for the power dissipation. Now 0.5 watts over 2.5 for the volts for the Zener voltage, you get 200 milliamps. This is the maximum possible Zener current in the reverse direction. Now, if I look at the electric characteristics for the first column, I see all of them in the type from this type all the way to that type. This is just given for this part, a partial of this datasheet. Now you see the Zener voltage at some specific Zener test current that is given. It's 2.5 in this case. You also, for this specific device, you can also see the minimum and the nominal and the maximum. So it is also listed, so it can fluctuate between these two values depending on what kind of device you have selected, because the manufacturer cannot guarantee that it will be exactly 2.5. It is between these two. Okay. Now the Zener voltage is then measured at specific test current as said before, so it is this current IZ, which is called a test current, in this case 20 milliamps. Now, for example, if I look at again this, I see that it ranges between 2.357 up to 2.625 volts for the Zener voltage. And then the nominal is 2.5 and as a test current is 20 milliamps. Now for the maximum, again, a maximum Zener impedance is measured also at this Zener test current. And that is given here, for this case, 30 ohms. And again for the test current of 20 milliamps. And you can also see the IZK, which is then the minimum Zener current is then 0.25 milliamps or 250 microamps. Okay, let's see an example. Always handy. Zener diode datasheet information. Now from this Zener diode type, we will read the following information. We see the maximum Zener impedance 24 ohms and also the Zener voltage, which is 3.6 volt at this 20 milliamps. And this is given here. This last row. You can see the information here. Okay. What you also see, by the way, is if I go down with my Zener current, so up to the IZK, which is the minimum, and lower, you can see the Zener impedance going from 24 all the way to 1000, so 1.7 kilo ohms. So it increases drastically. So we need to be careful also, stay in that safe region of the Zener current. Okay, let's calculate now the voltage across the Zener diode terminals. So between the anode and the cathode, when the Zener current is now 9 milliamps. So instead of 20 milliamps. So it changes because of some circuit parameters or anything else. And then we repeat the process or the question for 25 milliamps. So those are the two changes. So let's first look at the situation for the 9 milliamps. But again, repeat our model because the ZZ, the impedance for the Zener diode, is shown here. And we would like to calculate the voltage between these two nodes, cathode and anode. Now for the Zener current of 9 milliamps, we know that it is 11 milliamps smaller, so down from the test current, because test current was 20 milliamps, that was the nominated or rated current. So I go down by 11 milliamps. That means the following then, the change in the Zener current is then minus 11 milliamps if I look at the polarity. So I go down. Now, the variation in the Zener voltage is then given by this formula, because that is the change in the Zener voltage is equal to the change in the Zener current times the Zener impedance, just Ohm's law. Now, looking at the formula and also the 24 ohms maximum impedance, you will have this minus 264 millivolts. That is also the maximum variation, because this is maximum. Now, when you look at then the actual voltage between these two nodes, anode and the cathode, so from cathode to anode, then you have this. Since this is negative, we will go down. So it will be then 3.6 going down to 3.336 volts, so almost 3.34 volts. That is the decrease in the actual voltage between these two nodes. Now, when you go up, that means 25 milliamps, so that will be then 5 milliamps larger than the rated current for the Zener. Then the change in the Zener current will be then plus 5 milliamps. So the variation in the Zener voltage will be then given again by the same formula, will be then plus 120 millivolts. So you use exact same formula, but then you have the plus, so it will then go up. So we then 3.72 volts. So you go in this form. If you change your Zener current from 9 milliamps to 25 milliamps, you will change then the Zener voltage for this case between 3.34, let's say, to 3.72 volts. Okay, That's for this case. Now, let's also look at the simulation, because I simulated also this circuit using exact same type in the SPI simulator. You can see the type here, and also I just choose some input voltage Vs of 10 volts. And I also swapped the resistor value here and see what's happening. So I changed the resistor value and also measure the current through the Zener diode, also measure this voltage at this node, which is what we want. Okay, you can see the following information. The Zener current is now here 25 milliamps. That is the Zener current here, and that's the Zener voltage, and this is the resistance we change here, which is the R. Okay, for R is 20, let's say 255 ohms. I get 25 milliamps. For the exact same resistance here, I get 3.636 volts. We had 3.72, so it was a little bit larger in our case. Why? Because we have the maximum Zener impedance. It could be the case that in this model it is not at that moment the maximum Zener impedance, so it is not really a surprise. So these two are now linked together. Another one is 9 milliamps, so it happens or occurs at the specific resistance, 724.1 ohms. At the same resistance I have the Zener voltage, which is 3.483. Again, it is larger than what we have calculated. Again, because from the calculation we had this 9 and 25, and this was the nominal. And now we have the simulations, and these are the results. So you can see for the calculated part we are a little bit down, and from the calculated part for the maximum we also a little bit up. So we are a little bit up and down because of that maximum Zener impedance we have chosen. So in this case it could be the case that in the actual model for the SPICE it's not really 24 ohms but a little bit lower. Okay, let's also look at the Zener regulation, but then changing the input voltage. So we will vary this. So we have now a power supply here which will then produce a voltage between these two nodes, and we will now change that, so we'll increase it. So that will then increase the Zener current and also the resistor here to suppress or limit the current flow in the Zener diode, also the voltage. You can see it goes a little bit up. So the VZ, nominal voltage, plus delta VZ. So if the input is increasing or increases, the output voltage remains nearly constant because of the Zener current stays within the upper and the lower limits, which is given by this. So IZ is lower than the maximum and higher than the minimum value. But if I do the reverse, I will lower this, then IZ will also decrease, but I need to stay between these two limits. Then I will go down with my VZ, and the input decreases, but output voltage will remain nearly constant at that value, because we're staying between those two values. So the basic message here is, when you increase your input voltage, it will increase definitely the current here, but the voltage here across the Zener diode leads, also for this case, when you decrease it, must stay nearly constant. That is actually the regulation when you change the input voltage. Okay. Now the Vin max, the maximum possible voltage which you can put here, in this case, is then given by this. So that is increasing, so that will be then voltage across the resistor, plus the nominal voltage, plus the delta VZ, which is then given by the delta IZ times the Zener impedance. And for the minimum, because you go down, because you cannot just reduce the value up to some value, otherwise this is not regulating anymore, then this is the value. So this is the minimum and this is the maximum values for the input voltage. Okay, let's also look at the more details using the datasheet, and this is the circuit, and I'm now changing here the voltage. So it's kind of an example. If the input voltage is changing, you have resistor of 400 ohms, and we have now the Zener diode here, and that's this type. So for 1N522-9B, that's shown here, this one. Now it is now, if I look at the values, it will be then 0.5 again, because that was the maximum. Also same for this complete set, divided by the 4.3, which is shown here, and I will have my maximum current, which is on 116.3 milliamps. Now using Kirchhoff's current law at the input, we can say the input voltage is then given for this case, Vin is equal to VR plus the V out. But V out is now VZ. If I just ignore, let's say, the impedance of the Zener diode, and now it's 4.3 because it's shown here, then I can say V in is equal to VR plus VZ. Now for the minimum Zener current, I say this is the value I need to have in order to stay in the regulation. Then we have this expression, which is then V in minimum is IZK times R plus VZ. This is Ohm's law for the VR. Now if I now substitute the values, 0.00025, so it is then 250 microamps, which is then 0.25 milliamps here for IZK, times 400 plus 4.3, and you will get 4.4. So you go up by 100 millivolts in this case when you lower your input voltage. So that means actually the following: the lowest possible input voltage I can have is 4.4 volts. The maximum possible input voltage will be then calculated using the maximum Zener current, IZM. And we have already calculated that, so if I now substitute values, you can see the IZM times R plus VZ. And that will be then this. And if I now work it out, it will be then 50.8 volts. So I can say, conclusion, Zener diode can ideally regulate an input voltage between 4.4 and 50.8 volts. So if I change my input voltage between these two values, the regulation at the output is perfectly or nearly constant. And then the Zener diode will then maintain an approximate output voltage of 4.3. That is approximate. And since the Zener impedance was neglected here, that's why we have actually not taken into account, the actual output voltage will be a little bit different. So it will vary slightly compared to our calculations. But let's now look at an example against the same example in a more detail. So we get again this type, and we'd like to calculate the minimum and the maximum input voltage that can be regulated by this Zener voltage. So let's look at the solutions. We have the maximum power, so the minimum. First, the maximum Zener current, calculating again from the datasheet. And these are the values from the datasheet also. And if I now use this model, because now we will take that into account, so it wasn't taken into account, but now we will take the Zener impedance into account. Now you have the following model, and down the V out will be then the ZZ voltage and also the voltage where this is nominal. Now, using Kirchhoff's current law, at the input we can write down the following. V in is equal to the VR plus V out, and V out is equal to VZ plus a change in the VZ. And then the VZ, change in the VZ is change in the IZ times the ZZ. So the change in the Zener voltage is equal to change in the Zener current plus times the Zener impedance. Take this into together, and V in will be then expressed by this expression. So if we use this expression for the minimum and the maximum parts, for the minimum Zener current, for this we have then the following. It goes down, so it will IZK minus IZ. And this is an expression, you can just substitute this delta IZ in here, and you have the full expression here for the minimum input voltage you need to apply for this regulation. Now you have these values, and now into account taking also this 22 ohms for the maximum Zener impedance. Now you have 3.966 volts, approximately 4. Now for the maximum Zener current, we have then the following situation. We know it is delta IZ is delta IZM minus IZ. Now the maximum value is already calculated, and we know the nominal IZ and also the impedance for the Zener diode, so we have this. And if you calculate this, you will get 52.94 volts. So you can see the maximum and the minimum for the input voltage is different than what we have just calculated without the Zener impedance. So if you neglect that, these two values will be also different. So this is the range now for this example 5. So I can regulate the output when I stay with my input voltage between these two values. Okay. This is now the simulation result. You can see what's happening, and I have now exact same type here, and you can see I have swept the input voltage, so changing between 0 to all the way to 60 volts. This is the Zener voltage, the blue one, and this is the Zener current, which is the pink one. You can see it's sorting actually almost here, and the Zener current is here 0.001 0.573 milliamps, and then increase linearly and going to 120.5 milliamps for this specific voltage, because we said it must stay above 3.966 volts. That's actually shown here. So if I look at this, but the current is there not 0.25 milliamp, but it is 0.573 milliamps. So a little bit larger, or actually more than two times larger. You can also say, why is this happening? Because if I zoom in here, if I could zoom in here, I should actually go a little bit down with the voltage, and also this current will go down. So there is a slight error in this calculation, because the model is more accurate than what we have just used. We can see the Zener current here is 121 milliamps approximately. That's also a little bit lower than that, larger than that one, again, due to some errors in our actual calculations compared to the let's say, more accurate model in the SPICE. And this is the voltage for the maximum case. And if I go down, it's same situation. So if I use the same voltage here, I see the Zener voltage is 3.737. And if I look at this one, it will be then 4.726. So those two values are the, let's say, the values for this specific minimum and maximum. You can already see this is not really actually the starting point of the constant voltage regulation. It's actually starting here. So again, there is some slight error there. So it may be started at, let's say, 5 or maybe 5.1 volts for the input voltage, by the way, not for the Zener. Okay, that's for this example. Now let's look at the final topic, which is the Zener regulation, but then using the variable load resistor. This is the circuit we can have. It's the input voltage, resistor here, the Zener diode, but now we have a load which will then change. It can be an open in the extreme case, but it can be also short in another extreme case. So the Zener diode maintains a nearly constant voltage across the load as long as this Zener current here is between these two values for the minimum and the maximum. Now for open load, the load current is 0. All current must be then flowing through these two devices, R and the Zener diode. As the load is decreasing, so you go down, the load current IL will increase because this is getting shorter, and it will increase, and the Zener current IZ will then decrease because you get less current in here and more current through the, let's say, smaller resistor. So if this is, for example, in the impedance 22 ohms and this is going to the 1 ohms, then this is of course dominating in the current consumption. Now let's look at our example number 6. Will be our final example. We'll illustrate the Zener regulation where you have a variable load. Again, the same circuit. You see the Vin is 25 volts in this case. The resistor is 500 ohms, R, and we have a variable load RL. And there is a Zener diode here, and we have some parameters for the Zener diode. We assume it is ideal in terms of Zener impedance, so just 0. But there is a Zener voltage of 9 volts, and there is also a minimum Zener current, and there's also maximum Zener current, 2 milliamps and 60 milliamps for those two. We would like to calculate the range of the load resistor for which this Zener diode maintain the regulation for this circuit. Okay, let's look at the solutions. Now, for the minimum load current, that means IL minimum, the minimum load current occurs when the Zener current is maximum. So if this must be minimum, this must be then consuming the maximum possible current. That is, in this case, 60 milliamps. So let's say the following. We can say this I total current is just equal to IZ. So IL is completely 0. That means it is open. So we have no load actually there. That means the following, using the Ohm's law here, the voltage across this divided by its resistor will give you the current, because these currents are equal to each other. Will be then 25 minus 9 over 500 will give you 32 milliamps, but it's smaller than the IZM. So in the extreme case, I can say I stay below that value of 60 milliamps. But if I, of course, use another resistor, let's say 100 ohms, then this will of course go 5 times larger, and I cannot just say make it open. That is not possible. So I need to check this before I can say it is fine to have an open circuit or not. Otherwise, maybe I have some minimum over maximum value. So in this case, we can say since this IC is 32 milliamps lower than the maximum Zener current, it is allowed to have an open load. That means the minimum load current is 0. So this is the value. So thus the maximum allowed load resistor is in this case also infinite, so open. Okay, and this is the formula we can use that because we go for the IL minimum. For the maximum load current, IL maximum, we look at the maximum load current, but it occurs when the Zener current is minimum. So I cannot have here 0, so it must be minimum. That minimum is 2 milliamps, which is given here in the example. So then we have the following. IL maximum is this maximum current is then the total current minus the Zener current. But the total current was calculated as 32 milliamps in our case, so that will be then 32 milliamps minus 2 milliamps will be then 30 milliamps. This is the maximum load current. Now, using the value here, we can calculate how low the load resistor must be. Then you can calculate RL minimum, VZ, over the IL maximum, which will give you then this value, and then 9 over 0.03, 300 ohms. So that is, in this case, the minimum resistor you need to have in order to have this case, the regulation, let's say nearly constant at the output for this specific circuit, by the way. So if I change the circuit, I change this 25 or change this resistor of 500 ohm to a different value, you need to redo the calculation, also check if this is really possible so you can open it. So it is now between infinite and 300 ohms. That means the RL must be larger than 300 ohms. That is actually the conclusion for this example. If you have any questions, comments about this example, please let me know. I will try to answer them as soon as possible. See you next time in another video. Take care.